Hello students, welcome to EPG Pathshala. I am Dr. Nimisha Jadon from School of Studies Environmental Chemistry, Jivaji University, Gwalior. Today we are going to discuss about a module Chemical Equilibrium under the paper of Fundamentals of Analytical Chemistry. The learning objective of this module including the types of electrolytes, equilibrium calculations and the endpoint detection in titration. In a gravimetric analysis, the reaction used for the separation process must be so complete that an insignificant amount of analyte is left behind. We must know about the magnitude of the equilibrium constant of a reaction. For this, we apply principles of equilibrium to determine the feasibility of specific titrations. Now we discuss here about the equilibrium constants. The chemical reactions such as the formation of hydrogen iodide from hydrogen and iodine in the gaseous phase are generally reversible. For example, H2 gas reacts with I2 forms the 2HI. When the rate of the forward and the reverse reactions are equal, the concentrations of the reactant and the product remain constant with time. Hence, that the reaction has reached a state of equilibrium. In some cases, the concentrations of products are much larger than those of reactants. The equilibrium concentration reflects the intrinsic tendencies of the atoms to exist as molecules of reactant or product. Although there may be an infinite number of concentrations which satisfy the equilibrium conditions, there is only one general expression which is found to be constant at a given temperature of a reaction at a given temperature for a reaction at equilibrium. For the general reaction in aqueous solution, A aqueous plus B aqueous is in equilibrium and convert into the C aqueous plus D aqueous. This expression is also denoted as concentration of C and concentration of D divided by concentration of A and the concentration of B, that is equal to K, where K is the equilibrium constant. Here the brackets designate the concentrations in moles per liter, that is molarity at equilibrium. The fraction is often called the mass action expression. The term active mass to denote the amount of chemical reactivity. Chemists today use the term activity as the best meaning of active mass and the concentration as an approximation when the activity is not known. The concentrations employed are usually molality or molarity for reactions in aqueous solutions. For gases, molarity or the partial pressure is employed for the completely general reaction, that is small a capital A plus small b capital B is in equilibrium between C small c capital C plus small d capital D, and the equilibrium constant is denoted again with the concentration of C in aqueous and the C concentration and the concentration of D divided by concentration of A and B, that is equal to K. The exponents in this expression are the coefficients of the reactants and products in the balance equation for the reaction. Here in this table shows the equilibrium constant for various equations including the hydrolysis of acetic acid, then the aluminum hydroxide, then the reaction of tin and the cerium and the formation of silver chloride with the reaction of silver and chloride. If a reactant is a solid or liquid, its concentration
does not appear in the equilibrium expression. The reaction is that the concentration of a solid or liquid is constant. Increasing the amount of a solid or liquid in a reacting system does not change its concentration. The number of moles increases, but the volume also increases, and the number of moles per liter is unchanged.
Now we discuss here about the aqueous solutions. Water serves as the medium in which a wide variety of chemical reactions takes place. Weak and strong electrolytes are the combination of various acids and the bases. Aqueous solutions of certain compounds are good conductors of an electric current are called the electrolytes, whereas compounds whose aqueous solutions do not conduct current are called the non-electrolytes. For example, the sodium chloride is the good example of electrolyte, and the example of non-electrolyte is the ethylene glycol. The most ionic compounds are completely dissociated in water and are called strong electrolytes. Many covalent compounds dissociates to only a slight degree when dissolved in water and are called the weak electrolytes.
Here in this table, we have seen the strong and weak acid and bases in the aqueous solution. For example, weak acid is a strong acid is sulfuric acid, nitric acid, hydrochloric acid, and hypochlorous acid, and the weak acid including hydrogen sulfide, hydrogen carbonate, hydrogen fluoride, and acetic acid. Then the strong bases including sodium hydroxide, potassium hydroxide, barium hydroxide, and many more, and the weak acid including the aniline, amine, and the ammonia. We write equilibrium constants for the dissociation of weak electrolytes into ions and call them dissociation constants. For example, the dissociation of water is written as 2H2O is in equilibrium of H3O hydronium ion plus OH ion, that is hydroxide ion, and Kw is equal to the concentration of hydronium ion and the hydroxide ion. For acetic acid and ammonia, we can write the HOAC plus H2O is in equilibrium between hydronium ion and acetate ion, and Ka is equal to written as hydronium ion acetate ion divided by hydrogen acetic acid. Then the ammonia react with the water and form the ammonium ion and hydroxide ion. Then it is represented as KbNH4 plus ion concentration, OH ion concentration divided by NH3 ion concentration. Ka is used as a symbol for the dissociation constant of weak acid. Kb is used for a weak base, and Kw refers the dissociation of water and is sometimes called the protolysis constant of water. Now we discuss here about the salts. A salt is the product other than water formed when an acid reacts with the base. For example, when the hydrochloric acid and the sodium hydroxide react, the products are the salt, that is sodium chloride and water, written molecularly here as the HCl plus NaOH is equal to NaCl plus H2O. And when we written it is in ionic form, then H plus ion plus chloride ion plus sodium ion plus OH ion, then they form Na sodium ion plus chloride ion and the water molecule. The net ionic reaction is hydrogen is hydrated in water, then the hydronium ion H3O plus OH ion is equal to 2H2O. The NaCl is not a molecule but is a strong electrolyte completely dissociated into sodium ion and the chloride ions. Most salts are strong electrolyte. Their formulas molecularly as sodium sulfate, potassium nitrate, calcium chloride, etc. A few salts are weak electrolytes. One we will encounter later is mercury 2 chloride, that is mercury chloride. The reaction sufficiently complete at the equivalence point, that is Hg2 plus 2 Cl negative is equal to HgCl2. Now the reactions of salts of weak electrolyte. The salts of weak electrolytes react with water to produce either hydrogen or hydroxide ions. For example, an aqueous solution of the salt sodium acetate is basic because the acetate ion reacts with water to produce hydroxide ion, that is hydrolysis. It means the acetate ion react with water, form the acetic acid and plus OH ion. The reason is this reaction occurs to an appreciable extent is that the acetic acid is a weak acid and prefers to remain as molecules. The sodium ion does not react with water to produce NaOH molecules and H3O plus ions, since NaOH is a strong base and prefers to remain Na plus and OH ions. The salt ammonium chloride is acidic since the ammonium ions react with water to produce hydronium ions, that is NH4 plus H2O is equal to NH3 plus H3O plus. The chloride ion does not react with water to produce hydrochloric acid and the OH ion since the HCl is a strong acid. The equilibrium constant for the reaction of acetate ion with water is concentration of acetic acid, concentration of OH ion divided by concentration of acetate ion, that is equal to Kb. The symbol Kb is used to indicate that the acetate ion is a base. It is said that the acetate ion is the conjugated base of acetic acid. There is a simple relation between the Ka of an acid and the Kb of its conjugated base. This can be seen by multiplying the two expressions. H3O plus ion concentration, OAC ion concentration divided by HOAC ion concentration into HOAC ion concentration, OH ion concentration divided by OAC ion concentration, so that the concentration of acetate ion or acetic acid cut by their similar concentration, and the resulted reaction is that the hydronium ion react with OH ion, and that is equal to Kw. It means we can write it here as Ka into Kb is equal to Kw.
Now we discuss here about the activity and the activity coefficients. Strong electrolytes such as sodium chloride, though completely dissociated into sodium and the chlorine ion, they are independent particles in aqueous solutions. Physical properties of salt solutions such as conductivity and the freezing point suggest that the ions may be clustered together with the positive ions having more negative than the positive ion in their neighborhood. Under such conditions, the effectiveness of ions in determining the rate of chemical reactions is really important. Only in a very dilute solution are ions sufficiently free the influence of neighboring ion to act as independent particles. When we multiplied actual concentration by certain numbers called activity coefficient to obtain the effective concentration called the activities.
The activity of a species A is defined as follows. Small a concentration is equal to Fa capital A ion concentration, where small a in suffix capital A is the activity and F and A is in suffix the activity coefficient, and the concentration of capital A is the molarity of species A. For example, the activity of the hydronium ion is AH3O plus is equal to FH3O plus H3O ion concentration, and that of the hydroxide ion AOH negative is equal to FOH negative OH ion concentration. The true constant for the dissociation of water Kw is equal to AH3O plus into OH negative. Either the activity or the activity coefficient could be made dimensionless. Generally, it is the activity coefficient which is so treated. Hence, the activity expressed in the same unit as the concentration. The activity coefficients depends upon the size of the hydrated ions. Generally, smaller ions show greater departure from ideal behavior than do larger ones at the same ionic strength. Now we discuss here the Debye-Huckel Limiting Law. In 1923, Peter Debye and Eric Huckel presented a theory of interionic attraction effect which enables one to calculate activity coefficient theoretically. They assumed that ions were point charged at relatively large distances from each other, that the dielectric constant of the electrolyte solution was independent of the concentration of the solute, and that the dielectric constant of water could be used in all calculations. The equation is minus log Fi is equal to AZI2 under root micro, where Fi is the activity coefficient of a single ionic species such as sodium ion or chloride ion, Z is the charge of the ion, and micro is the ionic strength of the solution, and A is the constant. For water at 25 degrees centigrade, A, a collection of constant including temperature, the dielectric constant, and the Avogadro number is 0.512. The equation has been of great value in providing a law of extrapolation to zero concentration and is commonly referred to as Debye-Huckel Limiting Law. Now, the extended Debye-Huckel equation. The simple Debye-Huckel equation or the limiting law has been found to give useful results only in very dilute solution. As the ionic strength increases, mean activity coefficient calculated from the equation are significantly smaller than the experimental value. The Debye and Huckel later extended their theoretical treatment, assuming that ions are not point charges but have significant size. Hence, he derived the extended Debye-Huckel equation, where A is the diameter of the ion in angstrom unit and B in term which depends on the absolute temperature and the dielectric constant of the solvent, its value at 298 degree Kelvin using the dielectric constant of pure water, that is 0.328. So the equation is minus log F is equal to 0.512 ZA under root micro divided by 1 plus small a capital B, that is the concentration and the activity of the ions B, and the under root micro. The term A, sometimes called the ion size parameter, is said to correspond to the distance of closest approach of the cations and anions. There is considerable uncertainty about the magnitude of this term, but it seems to be about 3 angstrom for most singly charged ions and as large as 11 angstrom for ions of higher charge. Here the table gives some activity coefficient calculated from the extended Debye-Huckel equation and includes value of the effective diameter used in the calculations. Now we discuss about the thermodynamic equilibrium constant. In thermodynamic term, the true equilibrium constant, that is designated K naught, for the general reaction is depicted here by the equation. Here K represents the common equilibrium constant in terms of concentration, and it is often referred to as the concentration quotient. Since K naught is a true constant and since the activity coefficient of reactants and the products change with the ionic strength of a solution, the K is not strictly constant. However, at infinite dilution, the activity coefficients approach unity and K does become equal to K naught. Now we discuss here about the standard states. The reactants which are in aqueous solution and use of molarity as an approximation of the activity of such substances. Many of the reactions we encountered in analytical chemistry involve reactants which are gases, liquids or solids, and relation between activity and the free energy is given by the equation denoted here, where delta G is the free energy change for the transfer of 1 mole of a substance from a state of activity A1 to one of the activity A2. The free energy of a chemical species depends not only upon the nature and the quantity of the substance but also upon temperature and pressure. Hence, it is customary to adopt an arbitrary reference or standard state and to assign to it an activity of unit. Then values for the absolute free energy of an element or the free energy of formation of the compound can be calculated and tabulated. Equilibrium calculations. There are 4 types of chemical reaction used in titrimetric analysis. Number 1 is acid-base equilibria. The water is a weak electrolyte dissociating into hydronium and the hydroxide ion by this equation, and the extent of dissociation of water has been measured experimentally at 25 degrees centigrade. The hydronium and the hydroxide ion concentrations have been found to be 1 into 10 to the power minus 7 molar. This means that the value of Kw, the autoproteolysis constant of water, is 1 into 10 to the power minus 14 at 25 degrees centigrade, which is depicted here in the equation, and the values of Kw is discussed here in the table. The next is the solubility equilibria. The equilibrium constant expressing the solubility of a precipitate in water is the familiar solubility product constant. For a precipitate of silver chloride, the equilibrium constant of a reaction is given here in the equation, and the activity of solid AgCl is constant, and by convention take it to be unity. The solid is only slightly soluble, hence the concentration of silver and the chloride ions are small, and unless large concentration of other ions are present. Activities can be approximated by molarities. Giving the constant Ksp is called the solubility product constant. The general expression for the salt of dissociating is given here in the equation. The next one is the complex formation equilibria. The reaction involving complex formation are utilized by the chemist in both titrimetric and gravimetric procedure. The solid silver chloride will dissolve in a solution of ammonia. The equation can be written molecularly, that is depicted here, and the compound silver ammonium chloride is called a complex, and the complex is ionic, dissociating into silver nitrate ion and chloride ion, and the species silver nitrate is called a complex ion. The silver ammonia complex ion is formed in step by the addition of molecules of ammonia called the ligand and to silver ion called the central metal ion. Here the equation and the equilibrium constant depicted in the slide, and they are called the stability or the formation constant of the complexes. Now the next one is the oxidation reduction equilibria. The equilibrium constant of an oxidation reduction reaction is obtained from the potential of an appropriate galvanic cell. The equilibrium expressions for such reactions are formulated in the usual way. For example, when the iron 2 is titrated with cerium 4, the reaction is depicted here and its equilibrium constant also.
Here we are discussing about the systematic equilibrium calculations. To calculate the concentration of some species in an aqueous solution in which there are several interacting equilibria is known as the systematic equilibrium calculation. The mathematical calculation may be quite complex. However, there is a procedure called a systematic treatment of equilibrium which can be used in such a cases, and often reasonable assumptions can be made which greatly simplify the mathematical operations. The general approach is to identify all the chemical species in the solution and to find a set of equations sufficient in principle to permit calculations of the concentration of each species. When there are more equations than that can be solved simultaneously with convenience, hence invoke our chemical knowledge to simplify the mathematical problems.
The steps of the procedure included the identify all the species in the solution, then write all the equilibrium constants involving the unknown species, then write the mass balance or the material balance equation, then write the charge balance equation which is based on what is called the electroneutrality condition, and then using chemical principles make approximation to simplify the mathematical problems, and finally solve the equation for the unknown concentration. Then substitute them into the original equations to determine the validity of the approximation which were made. Now the next point is the endpoint detection in the titration. If the titration reaction goes well to completion, there will be a large abrupt change in the concentration of the analyte near the endpoint titration. The analyst can convert this abrupt change into a signal to stop the addition of the titrant. The equivalence point has been reached. Here is the table which shows the values of equilibrium constant of various titrations.
From the data in this table, it can be seen that the relative change in concentration of A is small at the start of the titration, and that the rate of change rapidly increases at the equivalence point is approached. If the titration is followed graphically by plotting concentration of A versus milliliter of B, this rapid rate of change is obscured because the linear concentration scale is not sufficiently large to reveal the enormous change that occurs. Since the concentration extends over several order of magnitude, it is the best displayed graphically by plotting a logarithmic function of the concentration PA is equal to minus log A against the volume of titrant. In such a plot called a titration curve, the value of PA rises slowly at the start of the titration rapidly increases as the equivalent point is approached and increases slowly after the equivalence point achieved. The values of PA are also shown in the table, where the change in PA per change in volume delta PA upon delta V can be seen to increase rapidly at the equivalence point.
Here again in this table contains data for the titration of 50 ml of 0.1 molar A with the 50 ml of 0.10 molar of B for the precipitation reaction. The reaction is A aqueous plus B aqueous forms the precipitate AB in the solution, and the values are depicted here. The figure shows the plot of concentration of A and the different dissociation constant of titration at the different value of titration of 50 ml of 0.1 molar A with the 0.1 molar B for 3 values of K.
Here we are discussing about the use of linear plots in titration. Sometimes the analyst does employ linear plots to depict a titration curve. Examples are photometric and the amperometric titrations. In such titrations, a physical property which is proportional to the concentration of the analyte or titrant is measured. If the titration reaction is essentially complete, the end point is easily determined by the intersection of two straight lines on either side of the equivalence point. If the reaction is appreciable incomplete, the curve will be rounded near the equivalence point. In this case, the end point is located by the intersection of the extrapolation of the straight line drawn through the points taken well before and after the equivalence point.
If these measurements are made well away from the equivalence, the axis analyte or the titrant will be sufficient to force the reaction to completion by the common ion effect. Then the point should be fall on a straight line, and extrapolation should yield an accurate determination of the equivalence point. Here is figure of linear titration curve of strong acid or strong base. As we add the titrant, the concentration of the analyzing analyte is decreases, and then the axis titrant is added, then again the activity of ion increases, and at the equivalence point, when we extrapolate the point, we will get the exact equivalence point of the reaction.
So at the end of this module, this module gives the information of one of the requirement for a reaction used in the titration is that it go essentially to completion at the equivalence point. We need to know the magnitude of the equilibrium constant of a reaction in order to calculate the degree to which the reaction goes to the completion under the given set of conditions. We also discuss here about the activity and the activity coefficient, solubility, and the various types of equilibrium processes. Thank you so much.